Log on, tune in, find out. Another good idea from Cambridge.
I'm talking about coercivity and integral factors.
All right. Thanks a lot, Simon. Thanks a lot, the organizers, for giving me a chance to talk here. So the title of the talk today is Coercivity, Non-Normality and Numerical Range of Boundary Integral Operators in High-Frequency Scattering. So there are quite a few concepts appearing today. Namely, first of all, coercivity. Then we are going to talk a little bit about non-normality as well. And we are going to see lots of different numerical ranges. And this here is actually joint work with you and Spence. And it is supported by an EPSRC Career Acceleration Fellowship. So let us dig right into it. So as a model problem, today I'm going to consider actually a very, very simple exterior scattering problem. Namely, we have a bounded obstacle here, omega, with some boundary gamma. Then we've got an incident wave coming in here, usually for very simple model problems here, just saying, okay, we've got an incoming plane wave. And then we want to solve the exterior sound source scattering problem. Namely, we want to solve delta u plus k squared u equals 0 in the exterior of omega with some zero boundary conditions on the boundary of our obstacle itself. And the complete total field u is decomposed into our incident wave, which is incoming, plus some scattered part, which goes out to infinity again. And for the outgoing part to infinity, we've got a Sommerfeld radiation condition. So that's a very simple modeling problem, but covering quite a few of interesting cases. And what we're actually interested in is the boundary integral formulation of this whole problem here and the ellipticity properties of the boundary integral formulation. Because if you just think about this partial differential equation here itself, delta u plus k squared u equals 0, we all know Helmholtz equation, it's an indefinite problem. If we were looking just at an interior problem with Dirichlet boundary conditions, would have eigenvalues on the real axis going into the negative part of the real axis. Here we're going to have, here the eigenvalue structure looks different, but it's still overall the same problem. We don't really have our nice ellipticity properties anymore for the Helmholtz equation. So the question is, what happens if you start looking at the boundary integral equation formulation of this? And let me just introduce this. So first of all, we can represent our total field u in the form of our incidence field minus the integral over the boundary of gamma, then our Green's function, which is Hankel function for the 0, then integrated over the normal derivative un of y ds. And the unknown function here is actually un on the boundary. And to compute un, we have to do the following steps. Namely, we need to solve the following equation. We have an operator a, k eta, un equals, and we have got to take 2 times normal derivative of the incident wave minus 2I eta, the incidence wave itself, where eta is the coupling parameter for a so-called combined integral equation formulation, where ak eta is the operator identity plus conjugate derivative of the single layer potential minus I eta, the single layer potential, having the following form here. So I'm not going to go into the details of these here, just want to show them once, but we're actually not going to need them again. The only real thing we're going to need in the talk is this ak eta itself over here. And that's the interesting object. Question is, what kind of spectral properties does ak eta have? Okay. So, and the properties that interest us specifically, these are actually coercivity properties and continuity properties of this ak eta. And let me just briefly reiterate these 2 properties. So it's really standard first chapter finite element book. Namely, we've got an Hilbert space H and some sesquilinear form on H. And then first of all, we want to have, one thing we'd like to have is certainly is continuity of a sesquilinear form, and very good if you also have coercivity of our sesquilinear form. And if you have those 2 things, then for the following standard variational problem, that we want to find some function u in our Hilbert space such that tuv equals f of u v for all elements in our Hilbert space, we then have the nice property that if you have some finite dimensional approximation, so some finite dimensional subspace, and we use a Galerkin framework, and UH is our Galerkin solution, then we can directly apply CS lemma, which gives us quasi-optimality of our Galerkin solution here, namely that norm of U minus UH smaller equals C divided by gamma in phi mom for all elements in a Hilbert space times norm of U minus V. So we can say, okay, there are different ways of establishing this, and CS lemma might actually not always be the best way, especially if you don't have coercivity. So we can use concepts like in subconstant, for example, to also establish quasi-optimality. But our motivation here, why we are actually going back to coercivity and ask the question about coercivity, is we are going to have very, very special spaces. Namely, the projects started off with the idea that we are not using function spaces anymore, which are just plain standard Galerkin spaces, but these are going to be very special hybrid, so-called hybrid approximation spaces with some oscillatory components, which directly aim at the solution itself. So they very, very badly discretize the operator, but they give us a very good representation of the solution itself. And since CS lemma is valid actually for any kind of finite dimensional space that you're putting in, we've got some great hope that applying CS lemma with some bounds on C and on gamma will give us some good estimates, K-dependent estimates on quasi-optimality. Okay. So in this talk specifically, we are going to consider certainly looking at our boundary integral operator. So our sesquilinear form is the form A of UV given by the A2 inner product with our operator here, and H is just the standard A2 space over the boundary. Okay. What are actually known results? Well, unfortunately, not too much. So the interesting question is really K-dependence. So dependence of the wave number, dependence of the continuity and coercivity constants on the wave number. So on the one hand, we've got this very, very nice results by Chandler White et al. In 2007. Namely, for the continuity, we've got this nice bound in terms of K if gamma is piecewise to C2, which is a mild assumption. So this is very nice. But for coercivity, it's much more difficult. So if we have a circle or a sphere in 3 dimensions, then for sufficiently large K, with a very, very sophisticated and integrate analysis of spectral analysis of the underlying operator, Dominguez et al. showed that we have a coercivity constant which is bounded below by 1. And on the other hand, if part of gamma is actually C1, then we also know that gamma smaller equals to 1. So for the circle, we know if K is sufficiently large, our coercivity constant is 1. And this is about the only domain right now for which you have an exact result for the coercivity constant. And very interesting, for a certain trapping domain, also in this 2007 paper, it was shown that there exists a sequence Kn such that the coercivity constant is actually decreasing with the rate k to the minus 910, which is also very interesting results. And we are going to come back numerically to this trapping domain. So theoretically, coercivity is quite a hard problem, but we'd like to know about this. So we're saying, okay, can we actually do some computations? Can we find out numerically what coercivity constants have to look like? And on that way, give us some conjectures actually about what we would like to prove at the end. And yes, fortunately, this is possible. Namely, by slightly reformulating this problem a little bit in terms of the problem of computing numerical ranges of operator. Now we are making the jump from coercivity down to the domain of spectral theory. And just to introduce a numerical range, so if T is a bounded linear operator, we've got some sesquilinear form here, given by the inner product of Tu with V, then the coercivity constant can just be written in this form here if our sesquilinear form is cursive. And if we look at this form here, and if you know a little bit about numerical ranges, then it becomes immediately clear that this is essentially has very much to do with the numerical range. Namely, if we look at the definition of a numerical range, this is the set of all values in the complex plane, inner product of Tu with U, where U is normalized to 1. This set of all elements in this complex plane. And if you just look at this definition here and the coercivity constant over here, we just have a very, very simple proposition, namely that the bilinear form T of UV is cursive if and only if 0 is not on the closure of W of t. So this is a very simple thing, but this gives us actually some way of doing some computations and actually computing the coercivity constants. Because about the numerical range itself, there's quite a lot known, especially in the spectral numerical and linear algebra community, and there's some very, very nice tools to actually estimate and compute numerical ranges. So our idea was to actually go down that route. So let's just briefly look at the numerical range. How does this look like for such an operator? Well, this is the numerical range of the operator on an equilateral triangle with wave number k equals 50 over here. And what we can see here very nicely, first of all, these black spots here, these black dots, these are eigenvalues of the discretized operator ak eta. I'm not going to talk too much about eigenvalues itself today. Just want to note to you that the eigenvalues here lie in the interior of the numerical range. The numerical range of the operator is this convex domain over here. And this x here, this actually marks a 0, and we can see here the x does not lie inside our numerical range, so our operator is nicely cursive. And by just looking numerically at the distance to this bounded set over here, we get the coercivity constant, the optimal coercivity constant. So this is our computational strategy. Okay, so let's just iterate some properties of the numerical range. First of all, it's got the very, very nice property, it's convex. Then the spectrum of t, bounded operator t, is contained in the closure of W of t. And very nice, the closure of the numerical range of a normal operator is the closed convex hull of its spectrum. So what you just saw on the previous picture, obviously it didn't seem to be a normal operator because the numerical range wasn't the closed convex hull of the spectrum. And in general, which is very interesting, for infinite dimensional operators, the numerical range is actually neither open nor closed, which provides some technical difficulties actually for convergence analysis there. So, and one simple proposition, if gamma is the unit circle, then ak eta is a normal operator. And this can actually be very, very simply shown by just going into the Fourier domain. What's a very interesting other question is the operator on the circle, is it the only normal operator? And that's an open question we actually haven't been able to answer yet. But it's got some nice consequences for the numerical range. Namely, first of all, if you look at the circle case, then it's really the closed convex hull of the spectrum. And if you look to some other domain, for example, a triangle, it looks really distinctively different over here. Okay, so the numerical range gives us not only some nice way of interpreting the coercivity constant, but it actually allows us some very, very nice reformulation of other theorems as well. It's quite interesting that we haven't really found them in books, even though it's just essentially, it's quite elegant to use this. So for example, if you go back to CS lemma, then we can reformulate CS lemma just using the numerical range very, very easily. Namely, we introduce the numerical radius, which is very defined, as the element with the largest absolute value in the numerical range. And one can also show, for example, in the book by Gustafsson, it's done that the numerical radius is actually equivalent to the norm of the operator. So if you just plug in the numerical radius, then I hope you can well see this, we actually get a symmetric form of CS lemma, which just depends here on the ratio of the element furthest away from 0 in the numerical range and the element closest to 0 in the numerical range. That's a much, much more symmetrical version than you usually find in books. Okay, but so much to that. So there are lots of nice other properties to do this. And I'm not going too much into details of computing the numerical range anymore, just to say it can be done, but it's computationally very demanding. The whole idea is that we are going to take Hermitian parts of the operator and always computing to get a left and right bound of the numerical range. We are computing the smallest eigenvalue of the Hermitian part of the operator and the largest eigenvalue of the Hermitian part of the operator. And then we are getting a bounding box which looks like this. So we know in what strip of the complex plane the numerical range must lie. And then by twisting the operator around and turning this, we can do this actually with other lines and add more and more lines. And on this way, we are getting, for example, if we multiply the operator I, we are getting these two additional lines. Just because the operator has become rotated, now I'm getting these lines. So we know the numerical range is in this square over here, this rectangle over here. And by just doing this on and on and on, we get a better and better approximation to the numerical range. So in the results I'm showing you later on, we actually use around 50 eigenvalue computations with the discretization of the boundary integral operator. Okay, we also have nice convergence properties of the numerical range. So first of all, you've got density in the sense that the numerical range of finite dimensional approximation actually comes closer and closer and closer the finer we get with our discretization to the numerical range of the operator itself. So this in itself is very well defined. Not going into details of the proof here. And we also have convergence estimates. Namely, if you use a very simple boundary element space with piecewise constant elements, diameter h, then we are going to get essentially linear convergence. So we've written this here down in the case that we have here a set W epsilon of A, which lies inside the numerical range, and is a set which almost fills up the numerical range up to a small distance of epsilon, so that we don't have to deal with the boundary. And then we always know that for a finite dimensional approximation, this set, which almost fills out the numerical range, is included in our set numerical range corresponding to the finite dimensional numerical range, plus some small circle around each point of the numerical range with radius c times h to the alpha. And if you're making h smaller and smaller and smaller, we're actually getting convergence to the numerical range of, to this set W epsilon of A. And since we can choose epsilon arbitrarily small, fill out our infinite dimensional numerical range as closely as we want to, we're actually getting convergence. So, and on sufficiently smooth domains, we can actually show that we've got quadratic convergence. So if you've got smooth domain, then it's all very nice and quadratically convergent. So how does it look like? So we've got convergence result here. This n here is actually the number of elements per wavelength. So I'm choosing here k equals 1, wavelength equals 1, just to demonstrate the rate of convergence, and n is the number of elements per wavelength. So the usual engineering rule of thumb here is 10 elements per wavelength is around here. If we just use piecewise constant elements, we've got this convergence curve which very nicely matches the n to the minus 2 curve, the quadratic convergence that we expected. If we go to higher order elements, certainly we are going to get better convergence rates, which is plotted here. Here, at some point, the convergence is stopping. This actually has to do with the fact that we are not approximating the numerical range itself, but we've got a polygonal approximation of the numerical range. And there's a small error coming in, which then gets into effect over here. Okay. So, okay, but I think maybe slowly come down to the results. So I'm not going to show this here anymore. On the square, the convergence is actually much more difficult, or maybe I still do show this. It's quite fun. So if we have, for example, the square as a domain, then so we've got corners, then everything gets much more interesting than in smooth domains. Namely, if you look at the convergence rate, so in the end we estimate at most linear convergence, but the effective convergence that we can observe here usually is initially much slower than linear convergence at the end. This is due to the fact, if one looks carefully through the proof, that for corner domains we are getting in some very large constants, and so one would have to go to h extremely small to get rid of this. Or if you don't want to have these large constants, I was writing there in the estimate h to the alpha, then alpha has to be chosen smaller than 1, namely closer to 0. And then we're getting smaller constant, and the effective convergence that we see is smaller than linear. If we choose, and that's what we've done actually at the end, quadratic basis functions with refinements towards the corners, and then if you can go to 10 elements per wavelength, we get around 2 digits of accuracy around here. This is at the end what we were doing. And this really has an effect. If we look, for example, here at the best numerical range that we could compute for the square with k equals 1 using piecewise constant basis functions, this is this here, and I think this was using 3,000 elements per wavelength, so a lot more than we can usually do. And if you go to an HP refined results, we're getting much better approximation. And this is essentially accurate. So by improving the number of elements per wavelength. This stays essentially the same. So it leads to such a result over here. So you see it's computationally demanding task. But let's go to the actual results. So this here is a kite shape, which is a very, very smooth domain, but it's non-convex. So the question is, do we have coercivity for this non-convex domain? And actually, yes, we do. It's very interesting. So if you look at the numerical range here for k equals 10, look at here, it's nicely bounded away from 0. If you look at k equals 50, k equals 100, it's still always the case. And the coercivity constant, that's the most astonishing result, is approximately equal to 1 independent of k, independent of the wave number. So up to numerical accuracy, we don't see any difference between k equals 10, 50, 100 in the distance here to 0. So this is a result which quite astonished us. And if we go to some other domains, here still a smooth domain. This domain here was interesting in the fact that here we still could observe coercivity, but at the end, the coercivity constant was slightly decreasing here. So for k equals 5, sorry, that's wrong. I was much too far. Okay, want to leave the surprise to the end. So this is the inverted ellipse, and for the inverted ellipse, we had the nice phenomenon that for k equals 10, 50, 100, comparing, the coercivity constant was actually shrinking quite a bit. And the question is still, is there a lower bound for k equals large enough for the coercivity constant, or will it converge towards 0? We have some reason to believe that there will be a lower bound for k equals large enough, which I will come to at the end. Okay, for polygonal domains, it actually behaves exactly the same. Here's the star-shaped domain, and here's even a very nice non-star-shaped domains. And again, the coercivity constant seems almost independent of the wave number, which is again very surprising, because one looks at analytic attempts to prove this, we usually distinguish between trying to prove something for convex, star shapes, and then, well, we haven't even dared looking further yet, but it seems to be relatively independent of the fact whether it's convex, star-shaped, or even non-star-shaped. And the most fascinating example of all those is really the trapping domain. The trapping domain, we call it trapping domain because it can trap modes over here. And the idea here is that if we close this cavity, then certainly we just have a rectangular-like domain, or here a square domain, and then we are getting real eigenvalues of the interior Dirichlet problem here, which are just multiples of k equals 5. So we have normalized the width of the cavity in such a way. And if you open it up, we still expect scattering poles of the open cavity which are close to the real axis and close to points of k equals multiples of k equals 5. So k equals 5, 10, and so on. So what happens close to these scattering poles? So let's look at k equals 4. K equals 4, everything is nice and cursive over here. And if you look at the eigenvalues, nothing is happening over here. But then we go to k equals 5, which is much, much closer to the scattering pole. And now we are becoming non-cursive. The coercivity constant, the 0 travels inside our numerical range, and we completely lose coercivity. Interesting fact is it doesn't have anything to do with the eigenvalues. If you just look at the eigenvalues, so at this spectrum of the operator here, then the eigenvalues always stay at the right side of 0, so they don't wander across. It's really a fact which strongly involves non-normality here. And then if you look at k equals 8, we are going away from a resonance again, we're going outside. It's again cursive. If you're coming closer to resonance again, we're losing coercivity again. What's theoretically clear? This is a spectral plot showing the scattering poles in the complex plane of this domain. Certainly, if we are at the scattering pole itself, then certainly we lose coercivity since we don't have injectivity. But the question is, if you just look on the real line, then what's still the effect on the real line of this loss of coercivity? So how far away from the scattering pole can we be to still have coercivity? That's an unanswered open question from these investigations. Okay, I'm not going into the summary of these results anymore. So you finishing off with two conjectures. First of all, what we conjectured at the end was that the combined boundary integral operator A is cursive on bounded domains for all wave numbers k which are sufficiently far away from a resonance. And the second conjecture that we ended up with is that the combined boundary integral operator A is cursive uniformly in K for sufficiently large wave numbers K for all non-trapping domains. So if you don't have scattering poles close to the real axis, then we hope that we will be uniform in KBs. And the reason for this, let me just show you at the end, is this results by Lex and Phillips, namely that for a non-trapping domain there are no resonances in the strip K with some alpha such that minus alpha smaller equals imaginary part of K smaller equals 0 for some constant alpha larger 0. So scattering poles are staying bounded away from the real axis, so we have strong reasons to believe that if you have a non-trapping domain, then if you have sufficiently large K, you're always going to be cursive, which is quite a fascinating result in itself if we compare this to standard finite element methods, where certainly we have to use very different tricks and don't have cursivity results. Okay, I've mentioned most of this. So one thing we are investigating right now and starting is really nice consequences for GM-RES iterations. So there's some very nice consequences which I'm not talking about right now. And if you want to see more about this and read up the proofs, we've got a preprint out. And certainly the talk by Ewan Spence on Friday, he's going to talk a little bit more about the analytic theory behind this. Thanks a lot.
Okay, so we have time for questions. Harry?
Right. This was fascinating, but I have a following question.
Yes.
Your operator A is identity plus a compact operator.
Only on smooth domains.
Okay, so take
Yes.
smooth.
Yes.
Okay. Now, for compact operator, if you are approximating the operator using the finite section method, we can obtain spectral convergence. In other words, you can, and of course, it is enough to look at the bounded side. No, it is not an accident that all your eigenvalues always congregate at 1.
Sure, certainly,
Yes,
because identity plus complex are shifted. Yeah.
Exactly. Now, so the point is as follows. Suppose that you are using some sort of fast convergence spectral basis,
Yeah.
Legendre, Polonais, Fourier, Chebyshev, depending on the nature of your boundary conditions. And this means that you can approximate, you can represent an infinite dimensional problem where you can approximate it very well
Yes.
by a matrix. And you can compute directly the numerical range of this matrix.
Yes.
So how this will be as a competition?
I mean, it's essentially, well, we're using, the basis that we're using is slightly worse than the basis that you're using, so we have to create larger matrices, since we're using a standard HP boundary element code to do this. So effectively, in order to get the same order of accuracy, we just have to use a higher number of basis functions, and we need to run our computer a little bit longer, what we did.
Yes, but I think it will be very attractive to show that even if you want to use finite elements, you need to use first spectral elements.
I mean, that's the optimal thing to do. I fully agree with that, yes. But our boundary element code, it just had implemented polynomials which are fine for domains with corners, and this is what we use at the yes.
Okay. Other questions? Okay, well, let's thank Timo once again for